Hello and welcome back to Calculus 1, section 4.4 on graphing functions. So tonight we unite algebra, pre-calculus, and calculus into this 13-step procedure, right, to graph functions. You will be able to graph, let's say, ln cosine x squared by hand if you want to, by using these steps. Now I see some of you are trying to figure out how to graph that. Well, of course you can't because we haven't learned the stuff yet. Now, some graphs that you are already familiar with, like x squared and x cubed and all of these things, right? We are not concerned with those at all, because you have those memorized from your pre-calc classes. What we are concerned with is all of that extraneous stuff that we want to graph. So first off, let's start with the list of, like a shopping list of all things that you need to do something like this. So we start, number one is the domain. Domain is necessary because you don't want to compute in the regions where the function doesn't exist. You know that, let's say, for ln function, you have your domain to be all positive numbers. Let's say an equation for critical points gave you -1 and +1. You don't have to waste your time with -1 because it's not in the domain. So knowing domain of the function helps you with that. Number two, this is now algebra. Find x and y intercepts. This is important. So x and y intercepts. And you find those when you set x equal to 0 or you set y. Actually, set, well, first y equals to 0 for x intercept, and then set x equal to 0 for y intercept. Then number 3, so those are our intercepts. Number 3 is we are moving to pre-calculus now with asymptotes. We have vertical asymptote, horizontal asymptote, and in some cases slant asymptote. If you need to, you do the limit. If you don't need to, just, go with what you have. So that's that. Now, number 4, we are moving into calculus. We will need the first and second derivatives computed so that we can go on and calculate all the other stuff. Good evening. And now, finally, number 5 would be the first derivative test. First derivative test. And you know what the first derivative test gives you, right? You have your critical numbers. Let's put points. So critical points, you have your increase, decrease, and for free, min, and max. So these are all the concepts from the first derivative test. Number 6 is the second derivative test, and that one is going to give us inflection points and concavity. So concave up, concave down. Number 7, if needed, additional points. Goody. And finally, number 8 is graph. Domain, x-intercept, y-intercept, vertical, horizontal, slant asymptote, first derivative, second derivative, increase, decrease, which gives min and max, second derivative test for inflection points, and then concavity, additional points, and then finally graph this. This is the shopping list of all things that you need to figure out before you graph a function by hand. Now, you might say, but why, right? If we can just go and assign x values and compute I assign x compute y's and then connect the dots just like in a coloring book. Why would we do this? Well, see, the trick is that functions have a part of a function that is interesting, and then the rest is all boring, right? Going in the same direction. What happens if that little squiggle, interesting squiggle, is happening at, let's say, 27, 28, 29, and all you tested is from -10 to +10? You don't see the interesting part of the function. This will, all of these things, critical points, and right, which give you min and max, all of those happen when the function does something interesting. When the function is boring, none of this stuff actually works. So this is an amazing part because it's not just letting you figure out what the actual function is, but it also pinpoints the regions at which we actually are supposed to focus on, right? And you can also calculate all of this by hand, meaning that, you know, in a case, you know, there is a cruise, and then you go to a cruise, you have an awesome time, and then something happens to the cruise, and you are the only one surviving to the island, right? There's no calculator, there's no cell phone. Wilson is not there either. So all you have is the sand and stick and your knowledge to graph these functions so you can build a shelter, right? Until the next person washes up, I guess. I don't know. Whatever is, I don't know what the deal. I've never done cruises and things, so I just, you know, I'm guessing that's the way it goes. Wait, what's the name of that actor from the movie with Tom Hanks, right? I realized that he only plays in the movies where he gets stranded somewhere. Did you notice that? Like, he was stranded at the airport and stranded at the island, and then stranded. It's interesting, right? Anyway. Yeah. We could, but it's too much. So let's run an example of the two examples of this, and then switch into review, and we'll do more examples next class after the exam. Apparently, in your infinite wisdom, you voted to have the exam next class, which is Thursday, in 2 days. So make sure you're here, or all right, good. Looking for something simple, like x minus 2 square root of x. You know, a good opening question. So what is the graph for this? By hand. Well, we start by figuring out the domain, right? The bad points. You see, x has all real numbers as domain. So you can take any number you can think of, positive, negative, fraction, decimal, whatever, pi, irrational numbers, and plug in for x. And the first part of the equation is good. The second one, the square root one, is the bad one because you can't use what? Negative numbers. So, to find the overall domain in a function that is combination of other functions, you have to find the most limiting domain, and that is domain for the whole thing. I like to explain it this way. You're at a train station. The train is leaving slowly. They haven't closed the door yet, right? If you do the light run, right, you can catch it. So no issue catching the train. However, with you is, and now you have a choice: leave this person behind or catch the train, right? You know what this is. Good. So the most restricting part of the domain is the domain for the whole thing, because we are nice people. right? Decent people. Make sense? So number one, what's the domain? Domain is 0 to positive infinity. This means that anything that we get in a negative range, we can ignore it. All of our partitioning for first and second derivative test will be done from 0 to positive infinity, which reduces our calculations and things we have to worry about. Number two, x-intercept is when we set y equal to 0. So x minus 2 root x equals 0. That's solving now equation. Now this is algebra equation. I believe in intermediate algebra it's like chapter 9 or something like that. So you guys should be able to solve this in your sleep. We square both sides to kill the square root. We get, so we square everywhere, and we have x squared is equal to 4x. Now to solve, we move everything to the left. Standard algebra stuff. And we have our two answers, x is equal to 0 and x is equal to 4. So we have two x-intercepts, 0, 0, and x equals to 4. Great. How about y-intercepts? Well, for y-intercept, we set x equal to 0. But then there's just going to be 0 minus 2 root 0, which is big 0. So we have y-intercept at 0, 0. Now, the rule of thumb is that as soon as you get x-intercept to be 0, 0, y-intercept must be 0, 0 as well. Right? You can only have one 0, 0 location. Number 3, asymptotes of all kinds. Well, polynomials, which is the first part of our equation, right? We have y equals x minus 2 root x. You see, participating functions don't have asymptotes. X doesn't have any asymptotes. Square root of x has no asymptotes of any kind. So, nova, noha, nosa. No asymptotes, so horizontal, vertical, slant asymptote, none of these are there because individual functions. Guys, this will change. If you had x minus ln x, ln x has a vertical asymptote at 0, right? So there will be asymptote there. Because we have a root x has no asymptotes, done. Also, if you have a rational function, denominator, x plus 1. There's a vertical asymptote at negative 1, right? You have to be very careful with asymptotes. And again, if there are any issues, you run the limits, right? You have the definition for vertical asymptote, limit definition for horizontal asymptote, and the slant asymptote happens only in the case of rational functions when the numerator has exponent by 1 bigger than the denominator. That's given. So no asymptotes of any kind. Number 4, first derivative, f prime of x is, derivative of x is
1.
Minus 2 times, and the derivative of square root is, I asked you to memorize this, 1 over 2 root x, nice. Please memorize this as the derivative of a square root so you don't have to go there and calculate stuff for 15 years. Memorize that as a square root. Now 2 and 2 dies. So we have our first derivative as 1 minus 1 over root x. You don't have to rationalize this because this x could be 4, and then square root of 4 is 2, right? No need to rationalize until you get like a root 3. Then you have to rationalize. But now root x could go anywhere, so just leave it. Now for second derivative, it's smart, right? For second derivative, it's smart to rewrite the function as 1 minus x to the negative 1/2, because this is the easiest way to take the derivative, right? When it's in exponent form like that. So what we do is the derivative of 1 is 0 minus, and then we take the derivative of 1 to the negative 1/2. So we take negative 1/2, x to the negative 3/2, and then the derivative of the inside is just 1, so we don't have to worry about it. So my second derivative is equal to 1 over 2x to the 3/2. We know from algebra that negative exponents are pushing x's downstairs to become a positive exponent, and then negative and negative makes a positive, so 1 over 2 raised to the 3/2. So now I have my first derivative right here, and I have my second derivative right here. So these are the two derivatives that I need. All right, so now we are already in the calculus portion. We took the derivatives, that's calculus. And now it's time for first derivative test. All right, first derivative test means take the first derivative and set it equal to 0 to find the critical points. So what do? I have 1 is equal to 1 over root x when you ship it to the other side. When you cross multiply, you get square root of x equals to 1. You square both sides, x equals to 1. We have our critical number. Remember that we are partitioning on this. I'm going to find its y value right away. So function computed at this, so that's going to be it's x minus 2 root x. So that's no coughing, 1 minus 2 square root of 1, which is negative 1. So we have 1, negative 1 as the critical point. 1, negative 1 is the critical point. Remember that the critical point is going to be either min or a max. It's going to be something. Great. We have one critical number, which is 1. We have no vertical asymptotes, and we have to partition from 0 to infinity. Let's go. A wall going to infinity, starting at 0, partition at 1 because of our critical number. Pick, because we have two regions, 0 to 1 and 1 to infinity, pick two critical test values. So 1/2 and 2. Let's go. First derivative calculated at 1/2. First derivative is 1 minus 1 over square root of 1/2. This is 1 minus. Do you guys see that this is this working the double fraction? Or do I actually have to go through elementary algebra over here? The top fraction is 1 over 1. The bottom fraction is square root of 1 over square root of 2. This is like the worst thing I wrote today. So this is a square root of 1 is 1. So you just have 1 minus root 2. I don't care what the value is. I know that root 2 is bigger than 1. So this is negative. If it's negative, we have a decrease over here. First derivative computed at 2. 1 minus 1 over root 2. Now this is going to be root 2 minus 1 over root 2, which is positive. So goes up. What I got for free is what? What did I get for free from this calculation? It's a minimum, thank you. So our critical point is a minimum. That's important, because how do you draw a minimum? You put a point and you put a smiley face through it, because if it's a smiley, it's a minimum. A frown is a max. So we'll deal with those as we go around. Right? It's a free piece of information that helps us guide the line. So we'll get there. All right, we're done with the first derivative test. We know that the function is decreasing, and then hits the minimum, and then increases. Number 6, second derivative test. Take the second derivative equally to 0. 1 over 2x to the 3 halves equal to 0. Well, what do we get? Cross multiply, you get 1 equal to 0. No solution, right? So no solution means no inflection points. We have no vertical asymptotes either. What does that mean? Does that mean we're not partitioning? No, that means everything is one partition. That's all it means. So I'm partitioning again 0 to infinity, but everything is one partition, so you can pick any value you want as test value. We'll pick number 1. And I have, what do I have? I have my second derivative now, computed at 1, which is 1 over 2 times 1 to the 3 halves. 1 to the 3 halves is just 1. So 1 half is larger than 0. So the entire thing is concave up. Concave up for the entire function. Nice. I'm not going to compute any additional points because I don't think I need them. I'm just going to draw the function, see what this looks like. X and Y. We start with our x-intercept. We have an x-intercept at 0, 0. So that's the dot that we put. And then the second intercept was at 4, 0. Okay? 1, 2, 3, 4. I'm using 2 squares over here as 1 unit. So I have these 2 points that the function goes through. The next point is our critical point, positive 1, negative 1. Positive 1, negative 1 is here. And I know I need to put a smiley through it because it's a minimum. The next order of business is to recall from first derivative test that the function is decreasing between 0 and 1. Great, connect that. There's the function decreasing. And then it's increasing after that, but it has to hit the 4. And what else do I know? The entire thing over here is concave up. And if you look at it, it is. It's concave up, right? So I have function start at 0, hit the minimum here at 1, negative 1, go through 4, and shoot up forever. It looks like check symbol, almost. It's not, but, you know, it's actually curved. And now, as every good student. If you care, we ask for the graph x minus 2 square root of x. There it is. Look at that. If you look to the graph, this is exactly what we had. Let me show one more time. What I have is, I start at 0, I hit 1, -1 minimum, shoot through 4, go forever up, everywhere concave up, 0 to 1 is decreasing, and then 1 to forever increasing. And now I go back to the graphing software, same thing. Starts at 0, 0, hits the minimum at 1, -1, goes to 4.0, shoots up forever, decrease, increase, always concave up. Cool, right? Of course, man. I know. You have to understand what power you get now. You can graph anything as long as you can take the derivatives and solve equations. Obviously, you can't do any of that stuff. Well, you can't do anything then. But this is, what we get. Before I switch, look at this. Problems 15 through 40 for you to practice polynomials, rational function, square roots, inverse tangent, ln of x squared. Maybe we can have fun with this one now. ln of x squared plus 1, that I'm not going to put on a test. Cosine x, sine minus x, and so on. A lot of these cool functions. Yes, what was the question?
What did the second derivative test tell us?
Concave up. So it's always like that. Holds the water. So let's run through one more example. Yes? Well, the first one gave you the location where the minimum happens. Second derivative helps. Remember we had the 3 pictures for the money investment, right? They were all increasing functions, but it was not enough. I need to know which way concavity bends. Right? Here. Somewhere over here are those graphs. There they are. You see, all of these graphs are starting at invested 10K. They're all increasing. Now, yeah, so do I bend this way or do I bend that way? Going up. So that's what a second derivative concavity will give you. Let's do one more example now, and then we'll do additional examples after exam. Bueno? Okay. So 36. Can do the one with ln, because it's fun. F of x equals to ln of x squared plus 1. Go on, show off your math skills for some time.
Well, Because natural law basically means one question.
I know I'm gonna need to. You mean to we're not going to take summer math class at the end? I get the sign 8 part. Yeah, that's right. No, I don't.
So that's the part where everything goes like ooh. All right, let's take a look at little bit, right, to get you over the pre-calculus humps, and then I know you can all take the derivatives. I know that the issue is in algebra. It's not. You don't have problems with calculus. No one ever does, right? But to find those x-intercepts, holy nightmare, right? All right, so we start with the domain. For square roots, logs, trig, any of these transcendental things, functions, this part is called an argument. Argument of square root, argument of a log, argument of sine. It's called argument in mathematics. To find the domain of this function, we know for log that argument must be larger than 0. So x squared plus 1 needs to be bigger than 0. That's what we're looking for. Now, when is x squared plus 1 bigger than 0? The answer is always. Because you can just see that from the graph. If you draw x squared going through 1, it's always above 0. Right? Because 0 is right here. And the whole thing is bigger than 0. So, domain is negative infinity to positive infinity. We get to worry about the entire domain. Also, you can do the trial and error thing. You say, try a positive number, 7. 7 plus 7 squared is 49 plus 1 is 50. ln of 50. I can do that. Try any negative number, like negative 3. Negative 3 squared is positive 9 plus 1 is 10. I can do that too. Maybe I have problem with 0. No, we don't, because 0 squared is 0 plus 1 is 1. ln of 1 is possible. It's 0, right? So no matter which number you pick, positive, negative, 0, they all work. That immediately says domain is all real numbers. Great. Number 2. X-intercept set y equal to 0. So we are solving equation ln of x squared plus 1 is equal to 0. From pre-calculus chapter 3, pre-calc 1 chapter 3, you know that you are supposed to e both sides. When you e both sides, you get x squared plus 1 is equal to 1. X squared equal to 0. X equals 0. So here is our 0, 0. And you know what? That's also at the same time x-intercept and y-intercept because it's 0, 0. Number 3, vertical asymptote. Vertical asymptote? No. See, you want to say yes. You want to say yes because you know that ln has a vertical asymptote, right? But didn't we just go through the domain and there were no interruptions in domain? Right? You see, that domain is good thing. So let's just, I'll just put here in blood, no. Let's just really quickly look at this. So if you have ln x graph, guys, goes like this, and there is a vertical asymptote as a y asymptote, right, x equals 0. But that's when this is x. Now I have ln of x squared plus 1. There is no way to make this negative. You can't make it negative. You can't even make it 0. Right? Using real number input. So that's why there is no vertical asymptote, even though you wanted it to be there because it's ln. Well, tough luck. In this particular case, no vertical asymptote, and you can immediately claim no vertical asymptote right here because there are no breaks in domain. By that talking, no ha, no sa. So no asymptotes of any kind in this case. Number 4. What's number 4? Derivatives? F prime of x is, hey, we're taking the derivative of ln. Isn't that the nicest thing in the galaxy? Copy the function as is downstairs, put its derivative on top, there you go. Copy the argument as is in denominator, put its derivative on top, we're done. Second derivative, quotient rule. By the way, are you going to use the logarithmic differentiation here? You can. There is no need for a sledgehammer if you don't need one, but maybe you like using sledgehammer all the time. By all means, go ahead. I'm just going to use regular quotient rule. And there you have it. Don't let this simple equation freak you out when it's set equal to 0. Remember the denominator always dies. So you can clearly see the answers are negative 1 and 1 from where you're standing, but that's okay. Number 5, first derivative test. This is where we set our first derivative, 2x over x squared plus 1 equal to 0, 2x equal to 0, x equal to 0. So now that x equal to 0, which we know it's 0, 0 as a critical point, is going to be min or a max. We partition domain is negative infinity and positive infinity. Pick our our test values. You can do negative 1 and 1. You can pick whatever you want. Doesn't matter. And what do we have? First derivative computed at negative 1. First derivative computed at negative 1, that's 2 times negative 1 divided by negative 1 squared plus 1. That's negative 2 over 2. Negative 1 less than 0. Decrease. First derivative computed at positive 1, 2 times 1, 1 squared plus 1, 2 over 2 equals to 1, larger than 0, increase. What we get for free is that our point over here is very good. It's a minimum. Why is it a minimum? Because we see it's a minimum. This shape must have a minimum. This type of shape has a maximum. So if you go down, you hit the bottom of the barrel, you bounce up, that's a minimum. Number 6, second derivative test. Now that's the longer equation. 2 minus 2x squared divided by x squared plus 1 squared. Again, this is intermediate algebra. Actually, we could have done a problem like this today. This is what I taught today. Rational equation. This is a rational equation. You solve this by cross multiplying. Cross multiplication is going to kill denominator. We have nothing to do there, right? So this is 2 minus 2x squared equals 0. I should keep this one for the test coming up for them, right? 2 minus. So now what do? We have 2x squared equals to 2, divide by 2, x squared equals to 1, x equals plus minus 1. Second derivative test gives us 2 values for partitioning. Partition, negative 1, 1, negative infinity to infinity, because we are on the entire domain. My test points, easy. Negative 2, 0, positive 2. 3 regions. Now, second derivative test. Second derivative computed at negative 2. Now, do you guys see that the denominator is squared? That will always produce a positive number. So I just need to make sure that top is either positive or negative. That's all it is. We only need positive or negative as the answer. We don't need the exact value. So I'm just going to say 2 times 2 minus 2 times negative 2 squared. Negative 2 squared is 4 times is negative 8. So this is negative divided by a positive. That's less than 0. Concave down on the first region. Second derivative computed at 0. 2 minus 0 divided by a positive number. That's positive divided by a positive. Larger than 0, concave up in the middle. And finally, second derivative computed at 2. It's going to be the same as the previous one because it was squared. And we have another concave down. Now, the only thing that we actually have to compute here are the y values for our inflection points, because we need to plot those. You have to know their y values. So now, here in blue, f of negative 1 is ln of negative 1 squared plus 1, which is ln 2. Good effort. And then f of positive 1 of coughing is 1 squared plus 1 is equal to also ln 2. So I have a point negative 1 ln 2 and positive 1 ln 2. So now what's our ln 2? It's about 0.7. So ln 2 is about 0.7. 0.693147 and so on. So it's about 0.7. It's good enough. We are ready to graph. At least I am. I don't know about you. You control your life. I have this negative 1, 0.7. So here and here. What else do I have? 0, 0 as a minimum. As soon as I draw that, I put a frown. Sorry, minimum, smiley. There we go. And what am I? So x, y intercept, that's it. That's all we have. So we have to work with this. So what do I know? I know that between negative 1 and 1, guys, look at this. Between a negative 1 and 1, function is concave up. Well, it better be because we have minimum at 0. So that means that this part has to be a smiley face like that. So I'm going to draw a curve through these. And then both of these have to be concave down, and they're increasing. If you look at our, right, that one is, something over here is off. So this is gonna go like that. That's the big point right there. This is 1 ln 2. And this is 1 negative 1 ln 2. Oh no, yeah, it's good because it's decreasing. What I'm talking about. Good. There we go. So now we're going to jump into Desmos. Run this real quick. I have ln, open parenthesis, x squared plus 1 and close. Ta-da, there it is. if you can see over here, -1, 0.7, +1, 0.7. Those are your ln. They are not labeled by the software, but they are right here. 2 inflection points. You have your minimum point right there. And you have the graph given. And it's the same as the one we did by hand. Depending on your knowledge, ability to solve equations, right? With e's and ln's and square roots and later trig next class, you will be able to graph pretty much anything. The alternative is always going to be the middle school, right, method, where you pick x's compute-wise and you connect the dots like in a coloring book, right? You don't have to color. Right? So this would be the part 1. Since next time we're going to do 2 or 3 examples of this, something obviously including trig as well. We might even push the part 2 of this lecture, or we might online, or we're just going to do examples in class and you download the notes. We'll see. There might be the part 2, the return on graphing. All right, bye.